Hello there. We are now ready to move on to page 3 in our math binders. So thank you to those that have been reaching out to me with questions. That's excellent. Keep doing that. You should have in your math binder now, you should have pages 1 and 2 all filled out. This is what it should look like. You've noticed with math class, you're watching videos, yes, but you're watching and you're doing as you watch. So you should absolutely be filling these out as you go and keep taking those pictures and sending them to me as you do that. So this is page 1, this is page 2, all filled out. We are now going to work on page 3 in your math binder, and I'm going to take it out so that I can more easily write on it. There's a chart on the top that I want to make sure you guys understand. All of the math practices that you've been doing, that hopefully you've been trying again if you need to, have had NS on them, and that's because we have been working in the number system strand of 7th grade. The number system strand takes a lot of things you already know about numbers from 5th and 6th grade and expands them to make sure you know everything you need to know about this part of the number system. Here's a little secret though, it's not the entire number system. You'll learn more in 8th grade. But here is the part of the number system that you guys should be familiar with right now. And it works its way out, and I'll explain what that means in just a second. So the very first, and this is historically how our numbers were developed, the very first numbers that we needed, that we use, that we understand are what we call the natural numbers or the counting numbers. Those are also the very first numbers that you learn when you're young. And the very first thing you do is you associate numbers with this idea of how many do we have, how many are there. And when you start counting, if I say, how many apples are there, or anything like that, when you start counting, you start with 1. You count 1, 2, 3. So the natural numbers or the counting numbers start with the number 1, and the dot, dot, dot means they go on forever. So I'm just going to circle these in different colors as I talk about them. So we have the natural numbers or the counting numbers. Now, historically, the next thing that happened is that people realized we need a value to represent what if I don't have anything. And that actually sounds so basic and simple to us because we're so used to that idea of 0 and nothing. But this idea of I need a value, a symbol, a number to represent it actually had to be historically identified. We had to say, oh, we need a value for this. And so this is the next set of numbers. It's called whole numbers. And the only difference is they add this number 0. Okay, so you have the natural numbers or the counting numbers that are just 1, 2, 3, 4, the numbers you learn when you're a toddler. And then when you add 0 to that, and instead of starting 1, you start at 0 and have this value to represent nothing and then count from there. That's what we call the whole numbers. So again, the only difference between natural numbers and whole numbers is that 0 is included. Now that's also why in this chart, natural numbers is inside of whole numbers. Here's what that tells you. If a number is classified as a natural number, you know it is automatically also classified as a whole number. So the number 3, you can see it's in this natural numbers category, but it's also in this whole numbers category. Okay, so the next one, as we reached out, the other thing historically as we kept developing different numbers is we realized, what if I owe somebody something or I'm missing something? We needed to represent values for that. And that's where we came up with negatives. And sometimes people call them negative whole numbers. Mathematically, that bugs me a little bit, but I understand why people say it, because whole numbers are their own category. There really is no such thing as negative whole numbers. But when you add the negatives to the list, you get this group called integers. And this group of integers, again, notice that integers totally encompasses whole numbers and natural numbers. So this chart works out. It does not work back in. And I'll explain that a little further, but let's first look at the last one. This last group here is this biggest box. And this final group really encompasses all the types of numbers that you are currently familiar with in the number system. You started naming these probably in 5th grade and have worked with them a lot through 6th grade. And all we need to do at this point is apply what you already know about these kind of numbers to the new rules that we've learned to help us be more efficient mathematicians. All we really have to do is put those things together. So this group is called rational numbers. And I want you to notice that the word ratio is right there in it. Even if you're like, rational numbers, that doesn't sound familiar. I know that you learned about ratios a lot last year. Ratios are a very big deal in the 6th grade core. And the word ratio is right there in rational numbers, okay? Because anything that is a ratio, and this is the big thing I want to make sure you connect in your head. Anything that is a ratio, which is a comparison of two numbers by division, those things can be written in all these different forms. Rational numbers are fractions, because a fraction, 1/4, 2/7, a fraction is a ratio. And any fraction, we're going to work on this a lot more this year, any fraction can also be written as a repeating or terminating decimal. Right now, what you need to understand is that anything that can be written in those forms, as a fraction, a repeating or terminating decimal, if it can be written that way, it fits in the rational number category. And it also, this purple box includes all of that. And some students then go, wait, Ms. McGowan, how can you even tell me one is a rational number? That's not a fraction. Well, can you write it that way? Absolutely. You could completely write 1 to 1, 1/1. You could write, let's change it to a different number, say 2. I could write the number 2 as a fraction, 2/1. I could write it as a terminating decimal, 2.0. Those are both examples of a rational number. So yes, the number 2 is actually a natural number. It's also a whole number. It's an integer, and it's a rational number. The chart works out. So wherever you start, so I might say the number 0. The number 0 is not a natural number, but it is a whole number. That means it's also an integer, and it's also a rational number. The chart works out, but it doesn't work back in. So if I say the number 1.5, 1.5 is a terminating decimal. Terminate means to stop. 1.5 is a terminating decimal. I just started right here in the purple box. I can't move back in. 1.5 is a rational number, but it's not an integer, it's not a whole number, it's not a natural number. So again, the chart works out. When you're naming things, if you start here, it's going to be an integer and it's going to be rational. But if you start here, it's an integer, but it's not whole number or natural. The chart works out, it does not work back in. Now, what I want you guys to do right now, and some people on these parts where I say pause the video and try, some people decide they want to switch to a pencil on that part just in case they get something wrong or confuse something, then they want to be able to erase it and change it. That's totally fine, you can do that. Or you can just keep writing with your pens, and you can even cross things out and add to it after when you actually watch the video, and that's always a good part of processing mathematics in your brain. So I want you guys right now, thinking of this chart we just talked through, I want you guys to try problems 1 through 6. I'm going to read them out loud to you right now so that you really are processing what they say, and then you're going to pause the video and try them. So question number 1 says, what is the difference between integer and rational number? So what's the difference between the stuff in this green box and the stuff in this purple box? Write out your answer to that. Number 2, is every rational number also an integer? Explain. Number 3, is every integer also a rational number? Explain that. Number 4, explain why the number 5 is considered a rational number. Number 5 says, in which number group or groups, because there could be more than one, does the number -8, that number is -8, in which number group or groups does the number -8 belong, and how do you know? And last one, in which number group or groups does the number, this is -2 3/4 belong? How do you know? Pause the video right now, answer those 6 questions, and then see how you did. Pause. Okay, let's see how we did. And you're welcome to change things, add things. If you worded things a little differently than me, that's totally fine. So question number 1, you can't read this. What is the difference between integer and rational number? Rational numbers include positive and negative fractions and decimals. They include all those ratios that look like ratios to us, but integers do not. Okay, so if you have something that's not a nice whole ratio, like 2 to 1, if you have something like 1 to 2, 1/2, 3.5, any of those things are considered rational numbers, but they are not considered integers. So with that in mind, is every rational number also an integer? Well, remember I told you the chart works out, it does not work in. So if I start with rational number, are all of these going to be these? No, because the chart doesn't go in. Here's an example. A fraction, any of those fraction parts of a number, like 1/4, 1/5, 1/7, that's a rational number, but it's not an integer. Integers are those whole pieces that you see on the number line, but not anything in between. So is every rational number also an integer? No. And I could write an example here, -2.7. Sometimes the mistake students make is that if they see negative, they tell me it's an integer. This is a rational number. Okay, it's not considered an integer. So a fraction is a rational number, but it's not an integer. Is every integer rational? Yes, because the chart works out. Every integer can be written as a rational number, but not every rational number can be written as an integer. The number 5 is considered rational because I can write it as a ratio, a fraction, 5 to 1. I can also write it as a terminating decimal, 5.0. Now, here's the big thing I want you to understand before I show you these last two. If you remember just this big purple box, the fact that all of them are inside, it's all that you need. You need to know that all the numbers that you're working with in 7th grade are all rational numbers. You are working with rational numbers. Now, most of last week, we focused on integers. We worked a lot with integers because it can be easier to learn and remember all the rules if we don't worry about bringing back in all the stuff about decimals and fractions just yet. So you did a lot with integers last week, but really you need to apply these rules. You need to expand it. You need to apply these rules to all rational numbers, which includes integers, but it includes more than that as well. So keep in mind for this number system, you are worried about all rational numbers. Again, we've been focusing on integers. Let's expand it. Okay, look at these last two. -8 is an integer, but it's also a rational number because the chart works out. -2 3/4 is a rational number, and it's just a rational number. Okay, your concern is rational numbers, and we are going to expand this now by remembering these things. And I know you don't have these written down yet, so you can pause it if you need to, but just some important reminders. You can color in these shapes if you feel like it, just for fun. But this says when you are adding decimals, the important thing is to line up the decimal. You've got to get those place values in order, and if you line up the decimal, you'll automatically do that. Place values have to go together with addition. Say that again, place values have to go together with addition. Now, that's also why when you're adding fractions, you have to get a common denominator, because that's actually making your place values the same, which we'll talk more about as we start converting these things. This is all stuff you learned in elementary. We learned some rules last week and we started to get good at them with integers. We now need to take what we learned about integers and what we know from elementary and just put it all together and make sure we can do that. Okay, so again, pause if you need to finish writing these down. When you're ready, flip over to page 4. Because really we are just practicing now putting our knowledge from elementary together with our rules. Okay, so I'm going to take you through the first 4 examples. Then you're going to pause and you're going to try the rest in pencil if you want to. Then you'll come back and watch and see how you're doing with remembering all this from elementary and applying our new rules. And when I say rules, remember I'm saying this. Same signs add, keep the common sign. Different signs subtract, take the sign of the one that goes farther. Farther from what? Farther from 0. Okay, so this is an integers problem. You did lots of them last week. There's not fractions or decimals here, so this is just like what we did last week. So I say to myself, same signs or different signs. I see different signs. Different signs subtract. I'm gonna borrow here, right? This is 68. Different signs subtract, because I had to borrow all the way down here, right? Different signs subtract. Take the sign of the one that goes farther. That's an integer problem. We practiced those a lot last week. Those rules still happen with all rational numbers. We just also have to remember some elementary stuff. For example, right here, I have decimals. I see different signs. Do you see different signs? Okay, good. I see different signs. I'm going to immediately tell myself which one goes farther from 0 because different signs is subtract. And when you subtract, you want the one farther from 0 on top when you show your scratch work here. 22 versus 24. 24 goes farther from 0. Okay, so I am subtracting. Why am I subtracting? Because they're different signs. Different signs subtract. All right, 8 minus 5, 4 minus 2, 2 minus 2. Okay, I got 2.3. Different signs subtract. Take the sign of the one that goes farther. I already decided 24 goes farther. It's positive. I put together my elementary knowledge of how decimals work with my 7th grade knowledge of how positives and negatives work. Rational numbers. The rules apply to all of it, okay? This one, look at this. This is integers. I don't have to line up decimals. I don't have to get common denominators. So what I'm going to do, oh, look at that, negative, negative, negative. This is all same signs. Same signs add, keep the common sign. 12 plus 4 plus 8. I'll just write this work over here for myself so I remember what I'm doing. But it's 12, 13, 14, 15, 16. I love to use my fingers. Use your fingers whenever you want. 16 plus 8 is what, 22? Same signs add, keep the common sign. 22. 24, Miss McGowan. Math is a mistake-making, risk-taking adventure. Negative 24. Okay, a fractions example. Fractions are everybody's favoriteest thing. Do you remember least common denominator? Again, none of this part is going to be new. It just might be a refresher. Okay, my main concern is that you understand how positives and negatives work, and I'll talk to you as we go through the notes over the next couple of days about, in real life, what's efficient. In real life, what does Miss McGowan use a calculator for, and what does Miss McGowan do by hand? Fractions like this, I honestly think, for me at this point, are faster by hand. When my decimals are like this, I can do them by hand. When they get long and crazy, I tend to type them in a calculator so I don't make human error. We'll talk about those things as we move forward. When is it reasonable to use a calculator? For this, what do 5 and 3 both go into? Does that sound familiar to you? I know they both go into 15. So the very first thing I do is I change those denominators to 15. Hope this sounds familiar. The next thing I do, because here's the new part for us, is the signs. You've done fractions, you've done this in elementary, but you haven't necessarily applied the positives and negatives to them yet. So how do I get from 5 to 15? I multiply by 3. So I need to do that on the top as well. 1 times 3 is 3. How do I get from 3 to 15? I times by 5. So 2 times 5. I'm doing this, remember, equivalent fractions. I'm keeping it equivalent, but making it work for my purposes. 2 times 5 is 10. So now the denominator just gets to stay. And now I can do exactly what I did with integers, just with the numerators. Remember, that's a fancy word for the top. I'm just going to look here, and I'm going to ignore the denominators, and I'm going to say same signs or different signs. After you go through your work to get common denominators, ask yourself, same signs or different signs, same rules. I see same signs, add, keep the common sign. Okay, you're going to pause the video one more time. Try the rest of these examples, come back and see how you did. And then we're going to just do a little bit of practice with rational numbers for your math practice tonight. But finish this page first, give it a try, pause, and come back. Okay, take a minute and look at problems 5 through 8. Do you remember stuff like this? How to change to a mixed number? I mean, from a mixed number to an improper fraction. Then I went 2 goes into 8, so I got my common denominators. You can leave this as improper or you can change it to mixed. This is fraction form. This is mixed form. And if you're writing these down or finding it, this is the point where you're like, I have no idea how you set that up or where you got that answer from. If you can tell from my work where it's coming from, write it down, feel good about it, move on. If you can't, you shoot me an email, you send me a message in Canvas, or you come over and ask me if you're in class. You'll still be able to see 7 and 8, but here is 9 and 10. For fractions, you get common denominators, and then you simply focus on same signs or different signs. This was different signs subtract, take the sign of the one that goes farther. For decimals, you gotta look same signs or different signs first, and that's sometimes what gets people mixed up. With fractions, you get your common denominators first, and then you focus on same signs or different signs. With decimals, you have to focus on same signs or different signs first, so you know if you're setting up an addition or subtraction problem when you line up those decimals. So different signs subtract, take the sign of one that goes farther. If you have any questions about those examples, please let me know. Otherwise, get this page finished and try your practice.